So this video is going to synopsize some of the work that we've done with span. And so span is a really big idea inside of linear algebra, particularly when we start working inside of vector spaces and working with vectors. So let's first define span. We're going to define the span of a set of vectors, v1, v2, v3, all the way to vn, as the set of all linear combinations of v1 through vn. And so consequently, what that looks like is it's going to be the set of all w's, okay? In this case, it equals, and we have a scalar c1 multiplied by one of the vectors, in this case, -1, 2, 1, plus a second vector, c2, times 3, -3, 2, plus c3, that's a third scalar, times 1, 0, 1. So anything that I can write as a linear combination of those three vectors is inside of the span. And we kind of conceptualize that visually or graphically as thinking about these are all of the different places inside of, in this case, R3 that I can get with these different vectors, right? So if I take a certain amount of one of the vectors and I add it to another amount of the second vector and I add it to another amount of the third vector, where can I get inside of R3? And that's how we conceptualize span. Then we have this other idea, which is that we say that a vector W is in the span, right? So this idea of in the span of V1 through Vn, if we can write W as a linear combination of V1, V2, and Vn, okay? Or what we'd say is we can write W equal to, and this is what we see, C1 V1 plus C2 V2 plus C3 V3 plus ... plus some CNVN, all right? So if we can somehow find the right scalars, all right, okay, some CIs, right, that belong to R, and we can construct this linear combination out of those CIs and the VIs, right, then what we end up with is a vector that's actually in the space. For example, is right? -2, 1, 3 in the span of -2, 1, 2, 1, 3, -3, 2, and 1, 0, 1. Okay. Well, it turns out it is because I can write -2, 1, 3, okay, equal to 7 halves times -1, 2, 1 plus 2 times 3, -3, 2 plus -9/2 times 1, 0, 1. And if you go in, you stop the video for a second, and you actually check, you'll see that that in fact is what it equals to. All right. So consequently, -2, 1, 3 is in the span of these three vectors, right? Because those scalars actually exist. So the question we might ask ourselves is, how do we determine if a vector is actually in the span of another set of vectors? So we need to show that there exists a solution to AX equals W. All right. So we have a theorem, and this theorem says that W is in the span of V1 through Vn if the solution to AX equals W is consistent, and where A is, and we call this the matrix of the column vectors. That's V1 through Vn, right? And the solution X is going to equal our C1, C2, all the way down to Cn. So our solution is actually going to end up being the scalars that we're looking for, all right, to give us the linear combination of these vectors V1 through Vn that make up W, all right? So basically the idea that we're asking here is we're saying, okay, does the C1s through Cns exist, all right? And what that means, the upshot of that is that if they exist, all right, then we're going to have a solution to this AX equals W because we can transform our vectors V1 through Vn, okay, into a matrix made up of those column vectors, right? Okay. Well, let's see how this actually works, all right? So if you look at this, we've got, what we want to get is we've got C1, right, C1 V1 plus C2 V2. Or actually, why don't we do this the other way around, right? Let's say we have A, right? And A was that matrix made up of the column vectors, V1, V2, all the way up to Vn, right? And we're going to multiply that by C1, C2, up through Cn. All right. Now, what we get here, all right, or what we're going to kind of understand is that remember that when we do matrix multiplication, we're going to multiply the rows times the columns. All right. So what we'll get is we're going to get C1, right? This is going to equal C1 V1, right? Where V1 is just the first component of this matrix. C1 V1 plus, and then C2 is going to be multiplied by, right, that second one. So it's C2, call it V2, right? Or C2 V22, whatever we want to call it, okay? And then we're going to do it so on and so forth until we hit the end, right? Which is Cn Vn. Yeah. And then we're going to do that for each one of our rows by each one of our columns. So what I'm going to end up with is I'm going to end up with, right, C1 is going to end up being multiplied by all of the values here, okay? All the values inside of that first column, right? C2 is going to be end up being multiplied by all the values inside of this column, right? So we end up with C2 times our V, or it's V21, V 22, right? Okay, right, all the way on down. So what I'm eventually going to end up with is that this thing here, okay, we can check it out again. You can go and try it out on a couple of them, is going to end up being C1 times that vector V1 plus C2 times the vector V2 plus like Cn times the vector Vn, right? Where that's Vn right there, okay? Great. And we want to see, is that going to equal, okay, we've got some vector B, all right? Okay, and so we'll call it, or actually we've been calling it W, haven't we? Equal to W. Now the question is, do these exist? And what you want to notice is that what we've done is we've set up a system, AX equals W, right? Okay, and if this system is consistent, that is that we have a solution. So if this system is consistent, then the scalars exist because X exists. That's what it means to have a solution. All right, so we say that W is in the span, belongs to the span of our set of vectors, in this case V1 through Vn. All right, cool. Now that's kind of the idea. So now the next question I want to ask is whether or not -2, -1, 3 is in the span of 1, 3, -1, 2, 2, 1, 0, 1, 3. And then if so, what is -2, 1, 3 written as a linear combination of 1, 3, -1, 2, 2, 1, and 0, 1, -3? So what I'm going to do is I'm going to set up my system. All right, I'll set up my system. Okay, and so my system is going to look like this. It's going to be 1, 3, -1, 2, 2, 1, 0, 1, 3, right? And then it's augmented with -2, 1, 3. All right, and we'll call this A augment B. All right, and I want to see, I'm going to take the RREF of A augment B. Okay, and this is going to equal, all right, so when I row reduce, what I get is I get 1, 0, 0, 2/3, 0, 1, 0, -4/3, 0, 0, 1, 5/3. All right, and as a solution to the system, what that is that's going to be x1 equals 2/3, or rather, let's use c1 because we're looking for scalars. C1 equals 2/3, C2 equals -4/3, C3 equals 5/3. Consequently, what that means is that we can write -2, 1, 3 equals, and that'll be 2/3 times this first vector, 1, 3, negative 1, plus negative 4/3 times 2, 2, 1, plus 5/3 times negative 2, 1, 3. And that is the linear combination, right, that forms negative 2, 1, 3. And so consequently, negative 2, 1, 3 is in the span of 1, 3, negative 1, 2, 2, 1, and negative 2, 1, 3. Let's check a different one. So let's say ask the question, is the vector 1, negative 1, 3, 4 in the span of negative 1, 3, 2, 1, and 2, 1, 2, 1? So our A here, our matrix of the column vectors, is going to end up being negative 1, 3, 2, 1, 2, 1, 2, 1. Okay? And so we're going to take AX equals B. We're going to try and solve AX equals, in this case, 1, negative 1, 3, 4. So we'll generate a matrix. Negative 1, 3, 2, 1, 2, 1, 2, 1. Augment with 1, negative 1, 3, 4. The REF of A augment B is going to end up equaling 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. This system is inconsistent. Okay? So there is no solution to AX equals B. And thus, negative, or excuse me, 1, negative 1, 3, 4 is not in the span of negative 1, 3, 2, 1, comma, 2, 1, 2, 1. So if we want to determine whether or not a vector is actually in the span of another set of vectors, we're going to construct a matrix out of the column vectors of the set of our vector space. Okay. Then what we're going to do is we're going to set up a system of equations, AX equals B, with the vector that we're looking for, whose linear combination that we're looking for, as a solution vector. Row reduce and see if that system is consistent. If the system is consistent, then our vector is in the span. If the system's not consistent, then our vector is not in the span of the other set of vectors, okay? And if it is in the set of vectors, then the solution represents the set of scalars that make up the linear combination. Now, a natural outgrowth or a natural question that a mathematician might have about this is that, well, if I could determine whether or not one vector is actually in the span of another set of vectors, is it possible to determine whether or not all of the vectors are in the set of another set of vectors? And so, like that natural question of whether or not we can write every vector as a set in a certain space as a linear combination of this set of vectors, right, is asking the question of whether or not this set of vectors spans that space or that subspace, that vector space or subspace. All right. And this is actually a really important question because oftentimes we want to know whether or not, I can create what's called a generating set, okay, for an entire space out of a certain set of vectors. All right. Now, if every vector in a vector space V can be written as a linear combination of a set of vectors, we say that that set of vectors spans V, right? So that's another one. We want to say it's, and notice that this one is spans is like a verb. In the other case, it was in the span, right? And span was a noun, right? So like it was the object is the span. It's like all the linear combinations that we can get from this set of vectors. In this case, we're asking whether or not they span, yes? And so what that's saying is that can we generate the entire space utilizing these particular sets of vectors? So like, for example, suppose that we have V, and we say, here's the set V is S times 1, negative 3, 1, plus T times 0, 1, 2, and S and T belonging to R. Well, what's clear is that if I pick an S, I'm going to get all the vectors on 1, negative 3, 1, right? And with t being 0, or if I pick s equaling 0, I get all the vectors along 0, 1, 2, okay? And then if I choose any ones, right, I get all of the linear combinations of these two vectors. So consequently, this set, right, spans V, right? Whatever V happens to be, okay? We're going to say it spans V. So let's dive a little bit deeper into this concept. All right, so let's say, for example, I've got this question. Does this set -1, 3, 1, 2, 2, 2, -1, 2, 1 span R3? So on the one hand, we're asking, can we construct a linear combination for every vector in R3 out of this particular set? And that's an important question, right? But on another level, what we're asking for is if A is a matrix of the column vectors, -1, 3, 1, 2, 2, 2, -1, 2, 1, all right, is AX equals B true for all B in R3? So if we picked an arbitrary B, right, we picked an arbitrary vector, and we tried to solve this system, yes, would we actually get a solution for every single one of the values, right? Okay, so basically, if I row reduce A, okay, am I going to get a matrix that tells me that I'm going to actually get a consistent value? I'm going to have a consistent system for all B. And we actually should ask ourselves, well, what would that look like, right? What would it possibly look like? And the first thing is that because we want to know consistency, the consistency of the system, what we need to know first is that there's going to be no 0 rows, right, inside of the row reduction, okay? So from chapter 2, we know that if we have no 0 rows in the RREF of A, then AX equals B is going to be consistent for all B. Another way to look at this is to say, that if A is an m by m matrix, then AX equals B is consistent for all B if the rank of A is equal to m, which is the number of rows. So when we take the RAF of the one that we just looked at, we end up with 1, 0, 0, 0, 1, 0, 0, 0, 1. The rank here is 3, right? It has no 0 rows, so what that tells me is that, in fact, I'm going to end up with a consistent system, right, for all B. Consequently, what that means is that every vector in R3, okay, is going to be written as a linear combination of these three vectors. So these three vectors, in fact, do span all of R3. And then it turns out the solutions to AX equals B, okay, are the scalars of the linear combination of -3, 1, -1, 3, 1, 2, 2, 2, and -1, 2, 1 that correspond to B. Since every single B has a solution, the scalars exist, and so every vector in R3 can be written as the linear combination of -1, 3, 1, 2, 2, 2, and -1, 2, 1. So what we say is that these three vectors, they span R3. Now, another thing that I wanted you to notice also is that A is invertible. So then by the invertible matrix theorem, there's a unique solution to AX equals B. So not only do we get a consistent system, right, which is great, because that tells me that the vectors span all of R3, but in this case, this special case, we end up with a unique solution to all AX equals B. So I want to ask the question, do these vectors actually span R3? So how I'm going to go about doing that is I'm in fact going to generate a matrix A, okay, equal to -1, 2, 2, 3, -1, 2, 2, 1, 2, 0, 1, 3. Then the RREF of A is equal to 1, 0, 0, 13 over 10, 0, 1, 0, 9 out of 10, 0, 0, 1, -7 over 10. When I look at this, the rank of A equals 3, right? No 0 rows. So AX equals B is consistent for all B. Consequently, my set spans R3. Excellent. There it is, right? We don't actually need to know what every single linear combination is. We just need to be able to answer the question whether or not we will find one for every single set. And the way that we do that, right, is we basically construct a matrix A, a coefficient matrix, right, and we see whether or not we're going to be able to generate consistent systems from that coefficient matrix. So this theorem kind of wraps up the idea that we're dealing with. Let V1 through Vk be vectors in Rn, then V1 through Vk spans Rn if and only if, for the matrix A equal to V1 through Vn, the linear system AC equals V is consistent for every V in Rn. So basically, is it the case that we can construct a consistent system from A C equals V for every single V? And basically the way that we know that is if we end up with the rank of the row reduction, or the rank of the matrix, excuse me, right? The number of zero rows, the number of non-zero rows in the row reduction, okay, is equal to the number of rows actually in the matrix. All right, and basically that allows us, that kind of gives us some way to think about a set of vectors, right? Okay, and to draw some conclusions about that set of vectors. All right, so let's recap. A vector W is in the set of vectors, is in a set of vectors if W can be written as a linear combination of that set of vectors, right? To show that W is in the span, we write the set of column vectors as a matrix and solve AC equals W. The vector C contains the scalars for the linear combination. If AC equals W is inconsistent, then W is not in the span of the column vectors of A. 2. If the span of a set of vectors is all of the vectors that can be written as a linear combination of the column vectors. So when we say that something is the span of a set, that's all the linear combinations that can be written as written using those vectors. Excuse me. A set of vectors S will span a vector space V if every vector in V can be written as a linear combination of the vectors of S. To show that the set of vectors span Rn, we'll write the set of vectors as a matrix A. A will be n by m, where m is the number of vectors in S. Okay? Excuse me. Yep. Then we're going to row reduce A, and if the rank of A equals n, that is the number of rows, then AC equals B is consistent for all B belonging to V. So S will span Rn. Right? Basically, what happens is that if we can find a consistent system for AC equals B for every B, then we know that we can generate the entire space, right? Okay, we can actually cover that space, right, using our vectors. All right, so this completes the mini lesson on span. Okay, next up, linear independence and dependence.